I hope you didn't go far, because we're back with the higher tier of probability. Now, you strapped in. What you'll probably find here is you will follow this right the way along. There are an awful lot of bits to it. Um, to follow right along, and then I'm going to show you the A star question at the end, and you're going to go, crap, really, maybe. Hopefully not, hopefully not, hopefully not. Okay, so probability, how does it change for higher tier? Well, the main difference, or the biggest difference, is this idea of conditional probability. And it's the idea of not replacing something back. So I might bring in a bag of sweets. It's usually the best way that I get it to illustrate it, because people like to eat sweets when I bring them in, and I can help explain this. So non-replacement. So a bag contains 3 red and 7 blue balls. A ball is picked, not replaced, and another picked. So complete the tree diagram. So what happens? Right. So the probability, there are 10 balls to choose from when picking the first ball. So probability of a red, there are 3 red and there are 10 balls. So the probability of a red is 3 over 10. Similarly for a blue, the probability of that is 7 over 10. Now, when I pick the second ball, whatever I picked on the first ball affects the second ball. So if I picked a red in the first ball and don't replace it, then there are only 2 red balls left. So the probability is 2 over what? Well, we didn't replace the first ball, so there's only 9 balls left in the bag. So the probability is 2 over 9. And the probability of the blue, there's still 7 blue balls in that bag. Then the probability of that will be 7 over 9. And in the last 3 diagrams, the bottom half mirrored the top. Well, that's not the case here. Because if we pick a blue first, there is still going to be 9 balls left. But there's are 3 red balls still. So the probability of a red is 3 over 9. And the probability of a blue is 6 over 9, because we took one out and didn't put it back. Now that's very different to what we've been doing beforehand. You have to think at every step of the tree. Think about cause and effect of what you're doing. What if we use this to solve questions? Now, we do it the same way as we did beforehand. So we've got to find the probability that we've got 2 red balls picked. And this is where you've got to use your language. The and or are very, very important. So 2 red balls are picked. There's only one way that can happen. We've got to use these 2 branches. So we've got to get a red ball and a red ball. So it's 3 over 10 times 2 over 9, which is 6 over 90, or 1 over 15. What's the probability of one of each colour? The same questions as have been kind of happened before. I can use both these ways. I can either pick a red and a blue, or a blue and a red. So we've got and in there, and or to add them. So we'll have 3 tenths plus 7 ninths using those branches, plus 7 over 10 plus 3 over 9 there. And if I do those all together, I get 21 over 90 plus 21 over 90, I get 42 over 90, which is 7 over 15. Okay. So if you think about it logically and you visualize it in your head, it'll actually make sense to you. If you look at it just the way it is, it might not, but that's it. Okay, so let's look at another example. A bag of sweets contains 2 toffees and 5 chocolates. A sweet is picked, eaten, and another picked. Complete the tree diagram. Well, I've already done that for you. But find the probability that both sweets are toffees and one of each sweet is picked. So 2 toffees and 5 chocolates. There's 7 in total. So there's 2 out of 7 and 5 over 7 are initial probabilities. If I pick a toffee and don't put it back, well, I eat it in this case. I've only 1 toffee left and only 6 sweets left, so it's 1 over 6 and 5 over 6. Similarly, if you eat a chocolate, don't put it back. I've still 2 toffees, 2 over 6 and 4 over 6. Probability that both sweets are toffees is probability of toffee and toffee, which is 2 over 7 and, or multiplied by 1 over 6, is 2 over 42 or 1 over 21. Probability of one of each is the 2 over 7 times 5 over 6 plus 5 over 7 times 2 over 6. That will give me 10 over 21. I'll let you work out this one. You can pause the video and then I'll display the answer. 5 white socks and 3 black socks are in a drawing. Stefan takes 2 socks at random. Work out the probability that Stefan takes out 2 socks the same colour. Here's your results. Okay. Let's look at something different. It's not always when we don't replace something back, right? So here's an example where a bag contains 3 blue beads, 5 yellow beads, and 2 green beads. Sid takes a bead at random from the bag, records it, and records its color and replaces it. He does this 2 more times. We've got to work out that of the 3 beads Sid takes, exactly 2 are blue. Now we could do a tree diagram, and if you do a tree diagram, you wouldn't be wrong, but it might take too long. Because it's not conditional probability, though, we can just list this like this. We can work out the ways that we can get exactly 2 blue. So we get 2 blues and yellow. We go blue, yellow, blue. We go yellow, blue, blue. We go blue, blue, green. We go blue, green, blue. Green, blue, blue. Right. Those are the 6 ways we can do it. Probability of a blue, blue, yellow. Well, the probability of a blue is going to be 3 out of the 10. 3 out of the 10. And then the yellow is 5 out of 10. We could do it like that. We're going to get that. The other ones are going to be exactly the same because it doesn't matter what order you multiply those in. So they're all going to be 45 over 1,000. And similarly, those 3, when I multiply those together, are all going to be like that. So the probability of exactly 2 blue is 3 times that plus 3 times that, which would give you a 189 over 1,000. Okay, now you could do it, and if it makes more sense to do it using a probability tree, it might help you work out all the possibilities. You can do it, but you would need extra paper for it, I would guess. You know, you wouldn't be able to do it any other way. For any match, the probabilities of each result for Villa are as follows: a half for a win, a third for a draw, and a sixth for a loss. Whoever made this was a big Villa fan, because that ain't true. Find the probability that in 3 matches will only win two matches, so they could go win, win, draw, win, draw, win, draw, win, win, or they go win, win, loss, win, loss, win, or loss, win, win. Same as before. Probability of a win, win, draw is 1 over 12, which is going to be the same for the other 2 as well. And similarly, the probability of a 1 win loss is 1 over 24. So exactly 2 wins is going to be the 3 times the 1 over 12 and the 3 times the 1 over 24. And that'll give you 3 over 8. Okie doke. There's another one for you to try yourself. Pause it, and the answers are as follows. Bit more complicated because they're using a different value for it, but very doable. Now what I'll just say is, rather than in the previous example I did 2.5 times 2.5 times 2.5, they might have written it out. 2.5 to the power 3, that's just all it means. You're multiplying the 2, 3, probability of the blue together 3 times, probability of 3 together 3 times. You'll get that, and you'll get that as your answer. Okay. Next topic. Expectation. This might actually be fairly straightforward. So expectation is the long run average you would get if a test was repeated many times. So you're going to take the probability and you're basically using it as a fraction. The definition is, if an event has probability p, the expectation in n trials is n multiplied by p, but we'll just see. It's using an estimate for how many times an event will occur. So a coin is passed, so the probability of throwing heads is 3/4. Dave is going to throw the coin 200 times. Work out and estimate that the number of times the coin lands on heads. We're just going to do your 3/4 times your 200, which kind of makes an awful lot of sense, but you might miss it, if you know what I mean. But the bit that you might miss is that idea is called expectation. So 3/4 of 200 is 150. Another example, there are 306 MPs in the Conservative parties. 4/5 of them say they support proposals to increase tuition fees. Work out an estimate for the number who will vote in favour of the charges. You're going to 4/5 times 306, which is 244.8. Now, as we noticed in the exam beforehand, that's not a number of people. We need to give round that in some way. So that's 245 people to the nearest whole number. Careful. 3 for you to try. I'll talk you through the first one, and then you can pause the rest. A coin is passed so that the probability of getting heads is 3/5. Dave is going to throw the coin 120 times. Work out an estimate for the number of times the coin lands on tails. 3/5 of 120 is for. It lands on tails. I did that wrong. If it's a heads, it's 3/5. If it's going to be a tails, it's going to be 2/5. So it's 120 times 2/5 equals 48. Pause. Try the next two. And your answers are. Okay. Expected winnings. Similar idea. Keith designs a game. It costs 160 to play the game. The probability of winning the game is 2/5, and the prize for each one is £3. 80 people play the game. Working out an estimate of the profit that Keith should expect to make. So profit is your takings take away your cost. So if your takings are 80 people times 160, you're going to take in £180. If there's only 2/5 of those 80 people, then only 32 are going to win, and 32 are going to win £3. So that's 96. Your estimated profit is going to be 128 minus 96. Starting to get a bit more complicated, isn't it? Each of the single things together aren't so bad, but you have to really think through the problems. It's very much a logic-based topic. It's probability. You really need to think about what's happening, what cause, what effect there is, and how you're going to get through it. There's a couple of questions here for you to try yourself. Pause. And there's the answers. Okay. Experimental probability. We're nearly there. Sometimes the probability of an event occurring is not understood, i.e. trying to predict the stock market. Experimental data can be collected to give an estimate of the actual probability. Right, think of this as the scientist, right? You've done a new type of experiment, and you want to use the results of that experiment to give a probability that it might happen again. So all you would do is if an event occurs X times in N trials, so say 10 times in 50 trials, the probability of that event is approximated by 10 over 50. So you've kind of made its own probability for it. I.e., Bob is convinced that his toast always lands butter side down when he drops it. He drops a piece of toast and it lands butter side down 30 and 50 attempts. Comment on his claim. It's probably 3 over 5. Bob's claim is supported by the data, although he has not conducted that many trials, so it's possible he was just unlucky. And that's exactly what you'd say. It's a bit like the questioning thing. What do you think? How could he improve his theory? Well, he could just do it more times. The more trials there are, the more likely it is that the experimental data matches the actual theory. Bob repeats the experiment, dropping the piece toast 1,000 times. It lands butter side down 600 times. Comment on his claim now. Still 3/5. Bob's claim is more strongly supported by the data, as it is very unlikely that he would be unlucky that many times. Okay. Problem solving. A bag, so some like exam type questions that are a bit harder. A bag contains red counters and blue counters. There are n red counters, and there is one more blue counter than red counter. Bob will take a counter at random from the bag and record the colour and pick another. The probability that Bob picks 2 red counters is 1 over 6. Prove that n equals 4. Or that there are 4 red counters. You need algebra for this. Okay. So, if the probability of if there are n red counters, it says there are 1 more blue counter than red counter, so your blue is going to be n plus 1. Okay, and that'll give you the total number of things that are in the bag. So that's n plus 1 equals 2n plus 1 is the total number of things in the bag. Next, probability that his first pick is a red is going to be n. So there's n bags, or n reds in the bag, and the total number of reds is 2n plus 1. What's the probability the second pick is going to be a red? Well, if he's picked 1 red, you're going to have n minus 1, and your probability, your conditional probability, is going to be the 2n plus 1 minus 1, which will give you 2n. Did tell you it's head pickling, didn't it? Now, this is very hard. Don't get me wrong, this is a standard question. What about the probability of both red? You would multiply those two things together. So you multiply n by n minus 1 and 2n plus 1 by 2n, and you would get that. You get n squared minus n on the top if you multiply it out. But what you could do is you could just cancel the n and the n top and bottom. And we'll come over that. N divided by n just gives you 1. So you'll have n plus 1 over 2 upon 2n plus 1, which is 4n plus 2. If you don't get this, stop the video. Especially if you didn't do algebra last year. This will scare the bejeez out of you. But I want you to have, for later on in the year, when we've come putting these together and you're trying to maybe think, right, I have a chance of an A or an A star here, especially. When your algebra is that bit better, we'll look at this and you'll go, right, I get this now. So pause it now if you're having a freak out attack. I will go through it in class again. And I'll probably try and use better, more physical objects to do it. The probability that they're both red is 1 over 6. So that is equal to that. If I cross multiply, I'll get that. Solve it down. I will get n equal to 4. That's very hard. Don't get me wrong. And like I say, I've said to you over and over again already, the purpose in those type of questions is to score some points. Could you have got the 2n plus 1 to be your total? Could you have got the probability that your first pick is red as that? You got a possibility the second pick is red. Even if you only got the first part, you got a point there. And think about what you would do with numbers as well. I'm going to put the second one up, although I don't really... God, I'm hesitant. Don't be spending too long on it if you don't get it. But there's your question. And your solutions are as follows. Okay. Now, you need to know quadratic equations. You need to be very good with your algebra there. But that's the solution. And that's the kind of standard of question that separates the real top from the very good. There's another one. Put up the answer. And that's why I say that probability gets to be one of the very hardest topics I think there is in the entire test, and why it's used an awful lot for the last question in the test. These are very, very tricky. You need to be very sure of what you're doing and your understanding of the topic, and that's exactly how it should be. I mean, if you're trying to separate the really best from the very good, you should try and really stretch them to see who really understands the process of what probability is and what conditional probability is, or about outcome of events or expectation. Who really understands it and who can apply it in this way. And that's why I didn't include probability in the exam that was just after Halloween there. I'll do one more, because I've seen this one come up before. The types of people watching the film at the cinema are shown in a table. So there are 21 adults who were male, 10 children who were male, 14 adults who were female, and 5 children were female. 2 of these people are chosen at random to receive free cinema tickets. Calculate the probability that the 2 people are adults of the same gender. So the first thing you got to do is add up all those together. So many people were together. There were 50. And it's conditional probability. So if I pick one person, a male, at random, an adult male, it's going to be 21 over 50. If I pick a second male, it's going to be 20 people out of the 49. Multiply those two together, I will get 6 over 35. If I do the same for the female, I'm going to 14 out of 50 and 13 out of 49. This gives me that. If I add those two together, I get that. And there's 4 marks for it. And that is very much a star standard question. Very difficult, but not impossible. You just have to know exactly what you're doing and be able to apply the probability theory very visually for yourself. What would you do? Actually consider yourself standing in front of those 50 people and going, right, if I take you out, what does that mean to everybody else? If I take you out, how many are left? How many meals are left? Well, if there was 21, I'd take a meal out, then there's only 20 meals left, but there's 49 people left, etc., etc., etc. The numbers get a bit more gaudier, a bit more scary than what they were before, but the principle of what you were doing on those early tree diagrams is exactly the same. I will be stunned if you don't have questions coming in to class. If everybody gets this first time, bravo. I will be the happiest person in the world, but I really think we'll see some people walk out of this class at the end of it and go, I just don't get that bit at the top. It doesn't really matter. This kind of higher tier stuff is for the very, very separation. It will not affect whether you get a B or not. If you can score some points, they're great, but yeah, good luck with it. Any questions, you can give me a wee buzz to me email, see me in class, any of those things, but good luck with it, and keep the spirits up, and I'll see you in class. See you later.
Lonely, broken hearted, life's not over. I can start again while I'm lonely, broken hearted. It's a hurting thing to get over.
I'm young, but I'm wise enough to know that you don't fall in love overnight. That's why I thought if I took my time, that everything in love would be right.
So as soon as I close my eyes, I was saying to love goodbye, but I guess I'm only broken hearted. Life's not over. I can start again while I'm lonely, broken hearted. It's a hurting thing to get over. No more empty conversation. Next time I will be totally sure. Oh, don't want the pain of falling in and out of love. It's more than my whole heart should know.
So I listen to all advice and remember each time I cry.
But I guess I'm only broken hearted. Life's not over. I can start again while I'm lonely, broken hearted. It's a hurting thing to get over. But as soon as I close my eyes,
And I remember each time I cry.
oh, never thought I'd be alone again. That's why I asked you to be my best friend. Don't you know you're always on my mind? I think about you all the time. I'm lonely, broken hearted. Life's not over. I can start again while I'm lonely, broken hearted. It's a hurt